like to listen to this recording or recording of any of our previous webinars that we've done the last couple months, those are available through our website at www.mallet.com. Mallet Technology, what we do is we use world-class engineering software tools combined with our broad knowledge and expertise to help our clients compete in today's marketplace to provide reliable and cost-effective products. We've been serving engineering customers for around 40 years. We started as an arm for Swanson Analysis Systems Incorporated, which was founded by Dr. John Swanson, as Swanson Engineering Associates Corp. In the mid-70s. And Swanson Engineering went on to become Swanson Analysis Systems, of course, changed their name eventually to ANSYS. And we've been an ANSYS channel partner since 1985, and our website is www.mallet.com. We will have more webinars. We'll keep the times the same. Fridays, 11 a.m. Eastern. Please contact me if you have any suggestions on what you would like to hear on our webinars. In the future, not only will I be emailing invitations to the webinars, but the webinars will be posted at the ANSYS main website, which is ansys.com, on their events page. And you can look there for the next webinar and upcoming webinars after that one. So again, thanks everyone for coming. We'll get started on today's webinar with Steve Rugg, our Technical Services Manager. Steve.
Okay, thanks, Boz. Okay, so I'm going to follow the process that I've used before. Essentially, I'll walk through a couple slides, and then I have some demo example problems to talk to. My goal in this webinar is to hit kind of what I'm going to call the biggest hitters that will help you attain convergence of some of the more challenging nonlinear contact problems you may encounter. So the goal of this webinar should be that it's very informative, different ways and tools that you have available to troubleshoot. These are kind of what I would term the most helpful. There are certainly other tools out there that will give you more minute details into what may be going on, but I'm just going to cover the basics and the most important, and then feel free to ask any other questions that you may have, and I'll do my best to answer them. So to get started, let's just cover the few contact formulations quickly, just so everyone kind of understands the differences between them, because this becomes important when trying to troubleshoot contact issues. So first contact formulation we'll talk about is pure penalty. Pure penalty is essentially it's a very straightforward, like Hooke's law equation for how the solver handles nonlinear contact. Essentially, it applies a stiffness associated with the amount of penetration that contact sees. The stiffness can be defined by the software or a user. We'll talk about how we may make considerations for when and where to apply those. The next contact formulation is called normal Lagrange. Normal Lagrange essentially adds another degree of freedom to the contact. It adds a forced normal degree, and it essentially enforces a perfect contact. So you're going to have almost zero penetration, subject to like computer error, right? So generally, if you're looking at a contact, you're looking at amount of penetration with a normal Lagrange formulation. Usually it's on the order of like 1 e to the -16th inches. So very, very small, small enough that it's meaningless. So this will provide an accurate solution in the normal direction. It doesn't necessarily have tangential degrees of freedom. The challenge with normal Lagrange is it does oftentimes make it harder to get convergence of nonlinear contact problems. So generally, and I'll talk more to kind of the step-by-step recommendations if you are having nonlinear contact problems, generally pure penalty is recommended. And I'll go into reasons why after I kind of finish these few slides. So the next formulation I wanted to talk to is augmented Lagrange. So essentially augmented Lagrange, this formulation just adds a extra Lagrangian term that essentially, let's say you have a contact where it has variable pressure throughout. There's some reasons where you're going to have very high pressures, other reasons where you may have low pressure. In this circumstance, you could set your normal contact pressure to be less, and you could allow the Lagrangian terms to help account for the excessive penetration at the higher pressure regions. So this is the ANSYS default contact formulation. It's fairly robust. However, generally, once again, when I'm having contact convergence issues, I will switch away from this to pure penalty because pure penalty is a much simpler, easier to control method, right? Where with the pure penalty method, if I step back to it, right, I have direct control over this K normal. With the augmented Lagrange, I do not have direct control over this Lagrangian term. Boz, can you work with John to get him an audio signal? Okay. So next up, let me go to the next slide. So the next up, so that's the contact formulation. So those would be of first importance when understanding context challenges. Those are usually the things you're changing first and foremost. Everything else is kind of lesser and mildly dependent on what formulation you're using. So the next piece I'm going to touch on is detection method. Detection method becomes important usually when you're trying to fine tune contact accuracy. So by default for pure penalty and augmented Lagrange, you use Gauss point detection. So essentially, if you have an element, all elements per finite element theory have Gauss points at specific locations in the element. The detection method for pure penalty and augmented Lagrange picks up the interaction of the Gauss points with the associated elements. There are options to switch away from this, right? You can switch away, so you can specify that the nodes are what pick up the contact with the other elements. You can do that usually. In all honesty, there's really two that I'll switch between on a regular basis, and I'll talk to the second one in a sec. The first, Gauss point, is a fairly robust solution, or fairly robust detection method. If you're trying to get slightly better contact pressures or things like that, I'd recommend switching to the nodal projected normal from contact, and I'll talk about what that does. The only time really it becomes beneficial to look at the nodal target is for methods where, or situations where you're having a corner impact a curved surface, right? So in this situation, we're going to have this element's going to drop through until this surface picks up these Gauss points, right? Obviously, that's probably potentially more contact than we want to allow. So if you do the nodal to surface instead, nodal normal from contact or nodal normal to target, these are better able to pick up that contact early and then address it. And I know I'm running through these quickly. I want to get to the ANSYS interface. Okay, and then the last, and this is what I talked about, that I usually switch either between Gauss point, and on Gauss points the program controlled, or nodal projected normal from contact. So the normal projected nodal from contact, what it does is essentially it takes the node, it projects the node to the corresponding contact surface, and it makes a calculation of how much elements overlap, and then it smears the resulting contact force for that node over the surrounding nodes, so you get a better distribution of that pressure. So this is a more computationally intensive approach. So potentially, depending on how much contact you have, it could make a noticeable impact on your solve speed. But generally, I'm of the mind where if I'm having contact issues, it doesn't hurt to try flipping it just to see what happens. Okay. So now this is really the guts of this webinar. So contact stiffness. Contact stiffness is really the best tool in your tool belt to help contact convergence issues. It's not the only tool, but it's probably the first thing to look at whenever you're having convergence issues. So within any contact setup, you can always you'll have this normal stiffness value setting. By default, this is a program controlled setting. However, the user does have full control to go in and either modify this setting via a multiplier, whether it's more or less, or you can directly input your own value. So this is, in this, like I said earlier, if we go back to the formulations, this applies to penalty and augment Lagrange. Normal Lagrange is a separate algorithm. It does not have a stiffness term. So stiffness is very important. I have several examples to talk to it. And so just to harp on this a little more, so the effective stiffness, if we picture like a pure penalty formulation, is essentially if you get penetration, so you get some initial penetration for a first iteration, on the next iteration, you're going to get a corresponding push back. And then you keep on iterating through that behavior until you arrive at some steady state that's acceptable relative to your allowable criteria. The challenge is if your contact stiffness is too large, there's potential that the model might oscillate, or it'll have a lot of trouble converging to a small enough penetration that's acceptable. And keep in mind, convergence behavior, typically the criteria that's the hardest to converge is force convergence. And so that's residual forces in the system that would make it not be at static equilibrium. So, or if you're talking transient, make it not be moving as predicted. So the higher the stiffness, obviously the higher the forces with more penetration. So higher contact stiffness is going to result in, if solved, lower penetrations of the contact, more accurate solutions. But it does make convergence harder. Okay. So I'll cover this at the end, but I want to step directly into ANSYS to talk to a few points. So, and chime in if anything isn't clear. Chime in and I can slow down and talk about it. So what I have set up here is just a very simple two-part problem, just replicated a number of times, where I essentially have a hole and then some corresponding shafts. There is 0.003 of an inch interference between the shaft and the hole. So 1.5 thou on each side of the shaft. And I'm trying to resolve that interface via a contact. So you can see in this case, I'm using a frictionless contact. And what I've done here is I wanted to show the impact of this stiffness factor. So I'm doing a frictionless contact. I've adjusted my formulation to pure penalty. And then I've gone in and I've adjusted the normal stiffness by a factor. And so what I've done is for this first block, this has a normal stiffness factor of 0.01. So it's taking the program generated stiffness and multiplying it by 0.01. The second block has a normal stiffness of 0.1, the third block of 1, and the fourth block of 10. So here, for these two, you're going to get less stiffness than the program specified. And for these two, you're going to get either equal or more. And then for the last block on the bottom, this I have a normal Lagrange contact applied. So this would give us the quote unquote perfect solution with no penetration. Once again, while that is great, the challenge with normal Lagrange is it can be hard to converge. And you don't necessarily have a lot of tools. You have less tools than either augmented Lagrange or pure penalty to kind of deal with that. So that's the basic setup. We have some mesh controls applied, but that's it, right? And then I just have the parts fixed in space, so I can just resolve only that interference. So if I go ahead and solve this, I'm going to see a couple things. First, keep in mind from left to right is lower contact stiffness to more contact stiffness. And then on the bottom left is augmented Lagrange. So immediately what I can see is if I have, for my lowest contact stiffness, odds are this is not acceptable. I can see that my results are significantly different than, let's say, my higher contact stiffness values, which will give me more accurate results inherently. And I expect, and we'll dig into it, I expect this is a result of the part-to-parts penetrating each other more. And so it's changing how much either the bore in this block is being expanded or how much the cylinder in the hole is being compressed. And I can illustrate that fact with a slight amplification. So you can see here, I've amplified all these the same. They all start with the same dimensions. So we can see that as penalty stiffness is increasing, we get more expansion of that hole or more compression of the shaft. And you can see once I get to a certain point, usually in the range of 1 or 10, or even with the augmented Lagrange, what I'm going to call my gross deformation, it kind of normalizes, right? It gets to a point where you could call the calculated behavior converged and accurate, right? So whenever we're talking about or considering modifying the contact stiffness, the first thing to check after you modify it, right? If you modify it, run the problem, it solves, that's great. There's a couple things that have to be checked to verify accuracy, right? One can definitely be stress, and you could do a convergence check where you slowly increase the contact stiffness to see if the stress changes. But the most basic is to look at the amount of penetration. So to do that, you just insert a contact tool. I'm having contact criteria show up for all my different contacts I've applied. This can show you a number of things. If you haven't played with this tool, I recommend it. You can look at frictional stress, pressure, sliding distance, and a number of other features. But so the first thing and really the most important is to look at the amount of penetration you get that contact, right? Because inherently we know that penetration between two bodies is a non-real phenomena. So our goal with simulation is to minimize that phenomena so we get accurate results. So if I look at my results here, I can very, very quickly see that my body with the lowest contact stiffness has the most penetration. And so here we're looking at essentially 0.6 of an inch. And when my interference is only 3 thou, that's a fair portion of the interference that I'm just losing because the bodies are penetrating. If I look at my increasing stiffness, right, this very quickly gets to a point where my penetrations get smaller. Here I'm almost an order of magnitude smaller. Here I'm more than order of magnitude, and here I'm almost 2 orders of magnitude smaller than the original, right? And once you're at the point where I'm talking about micrometers, or sorry, microinches, generally, depending on your problem, everything depends on your problem, right? But for a problem like this, I would assess this as accurate. If I really wanted to truly check it, I could look at my normal Lagrange result, right? And you can see here, I have 2 e to the minus 16th inches of penetration, so essentially a near perfect solution. So if I can compare, let's say, the contact pressure between my results, here I'm at 32, 34, 32, 29, 18, right? So to some extent, this is program default, so this is the penalty stiffness of 1. I would qualify this as accurate, accurate enough, right? Increasing penalty stiffness this is just rough probe location, so it doesn't directly correspond. But generally, the more higher contact stiffness, the more accurate it's going to be. There may be some element-to-element contact weirdness that's going on in this case. Results, I would qualify as accurate. This one, let's say you're talking, I don't know, 5% accuracy, something like that. Maybe you could validate that as good, but if you can increase the contact and get a more accurate answer, it's recommended. We can easily see that if we have too little contact, our results not accurate at all. Okay. So that is the first example. And what I want to I'm going to step to the next example, and it's different for an intended reason. So the way that ANSYS generates, or the way I perceive ANSYS's default contact stiffness between bodies as, is that essentially it's great and it works really well when you have bolted joints or press fits or other phenomena of similar contact intensity. Oftentimes in my simulations, I very commonly change the contact stiffness to a much lower value because I don't necessarily have those phenomena going on, and the default contact stiffness is far, far too high. So that leads me to my next example. So for this next example, we essentially have a beam in space floating above a plate. The end of the beam is fixed, the bottom of the plate is fixed, and then I have a load applied to a span near the end of the beam, but not right at the end, right? In between each of these plates, I essentially have a contact region to pick up contact between the lower side of the beam and the plate. So you can picture in this case that the amount of force interacting between the beam and the plate is going to be dramatically less than like a bolted joint. And then the other caveat is, for a problem like this, we have to consider how much does penetration impact our result, right? In our first example, the amount of penetration we had has a dramatic impact on the result. For the second example, we may find that has a significantly, we will find that it has a significantly lower impact than the other one. So I've set this up in a very similar way. If I walk through my contacts, just the baseline, I have a frictionless contact between the two bodies. I've assigned pure penalty. And in this case, I've assigned an absolute value. I know just from experience, for a beam bending problem like this, I can get reasonable accuracy in my result with a normal stiffness value in the range of 100 to 1,000 Newton per millimeter cubed. Once again, that should always be checked. That's just, I know to try that as an initial value. So I've assigned that to start. And then last, there's enough separation between these two bodies that I've assigned a pinball sufficiently large to pick up the other body. If I don't assign this and I try to ramp to full load immediately, what happens is my cantilevered beam never picks up this contact, blows directly through it, and I get a result that's meaningless to me. Right? There's other ways around that. I could ramp the load slower and gradually pick up that contact. But in this case, I know it's not necessary. I increase the pinball size and I pick it up immediately. And so then what I've done for the rest of the contacts, that's the first. For the rest, I've just gone down and you can see I've increased each setup by an order of magnitude for the normal stiffness value. So I have 2,000 newtons per millimeter cubed, 20,000 newtons per millimeter cubed, and then 200,000 newtons per millimeter cubed. And then I just have a fairly coarse mesh, but 2 millimeters of thickness on the beam. I have my load applied. It's essentially 200 pounds on each beam. And then I go ahead and solve it. And you can see here, I did have to go through a number of iterations to get this to solve. However, I will tell you just off the bat, those iterations resulted from the highest stiffness setup. If I were to express everything right now, and I can in a second after I walk through the results, and it was only to leave this first setup active with the lower penalty stiffness or lower contact stiffness, it would solve in 2 to 3 iterations versus the 23 that the higher stiffness solution drove. So that's the setup. Let's look at the implications of the varying stiffness in this type of behavior, right? So this circumstance is more of a beam bending contact. I would define it as beam bending contact versus like a bolted joint. So in this case, if I look at my deformations, these all look relatively accurate, relatively the same. I could probably query the end of all of them. 5.52 inches, 5.57 inches, 5.5, 5.6 inches, and then, and keep in mind, some of what's impacting this is my query location, 5.6 inches, right? So they're almost all exactly the same. The next thing I could look at is stress. Usually that's what I'm interested in anyways. If I just hover over them, I can very quickly see that my stress regions are nearly identical between all the different setups. And so then let me look at the amount of penetration I get in each of them. So I can very quickly see that for each of these setups, I get the most penetration as expected on the setup with the least amount of stiffness. So that's on the left. And then I get the least amount of penetration on the setup with the most stiffness. So that makes sense. However, right, the caveat here is in this case, this amount of penetration does not necessarily have a dramatic impact on the result. So for this amount of penetration, let me switch my units here. So I have 0.02 of an inch penetration for the least stiff contact stiffness. However, I'm looking at a total deformation of 0.125 inches, right? So pretty much 1% penetration ish. That amount of penetration in this setup doesn't impact my stress results in a dramatic way, right? And so if I'm having trouble, it's okay for me to decrease that contact stiffness without jeopardizing my results, particularly for FEA simulations, which are known to be accurate to 5 or 10%, and definitely always are going to be different than a produced model, given machining constraints and material properties and all those different factors. So in this case, it's fully okay for me to decrease the contact stiffness. Certainly if I went too low, I certainly could go too low and it would affect the stress results. However, relative to what the program would default to, this is significantly less. And I can demonstrate that. So what I've just showed, this is 200 newtons per millimeter cubed to 200,000 newtons per millimeter cubed. I have a fifth system that I'll unsuppress right now, which, let's see, if I run this, let me go ahead and suppress these other things. Just reapplying a couple things. Okay. So if I run this system is program controlled for everything. It's program controlled formulation, program controlled normal stiffness, and program controlled, and the only thing I've specified is the pinball radius so that it detects that surface. So if I run this problem with the program setup for everything, what I'm going to see once it starts iterating is essentially the default program controlled stiffness is so high that I actually cannot get a converged solution, right? And so this is why I say that program controlled stiffness is really perfect for bolted joints or other similar connections. But for this type of behavior, it's not appropriate. It allows for too much contact convergence challenges. So this is going to continue to iterate. It's going to continue to bisect and bisect and bisect and never converge. And if I look at, and so I'm going to interrupt this solution. If I go into my solver output file, and if you've never dug into solver output and understand kind of what it holds and how to read it, it's certainly beneficial and worth your time to do so. So I do recommend it. But if I look at this output file, first thing I can see is my real constant for the contact active right now is 4 and 3. I'm going to scroll down just a little, and then I can see here my resulting initial contact stiffness value. I don't have the other systems active right now, so we can't compare to their values, but I can tell you that this value that the program automatically defined is an order of magnitude greater than what I ran on any of the other systems, right? So essentially, just a reminder, this was 200 Newton millimeters. This was 200,000 newtons per millimeter cubed. This system, the program defaulted to a value of 2 million newtons per millimeter cubed for the stiffness. And once again, even with 200, we really get accurate results for the system. And the 2 million resulted in us not being able to get any solution. So when, all that to say, when modifying contact stiffness, and it's really the first thing to check when you are having contact difficulties, convergence difficulties, you have to, one, understand what type of joint you have or what type of contact you have. And then two, if you do decrease the stiffness, make sure you analyze the penetration, make sure that's acceptable, and then also try increasing the stiffness and getting a converged solution to try to compare results between the two. If results between the two, stress results primarily, deformation is not usually that informative, are similar or the same, then you know that the lower contact value, which probably results in fewer iterations, is likely acceptable. Okay, so that kind of wraps up the two examples. I just wanted to touch on the tools available to you to help try to troubleshoot contact issues. So I'm going to do a couple things. I'm going to suppress this. Just going to reapply my force. And that's it. So the first tool is solver output. Definitely dig in that and look through it. But the second and really more important tool is the force convergence plot. generally, if you have a nonlinear solution, I would recommend always having this open. This is a measure of how much non-real forces are remaining in the system prior to a converged solution. So this problem is in static equilibrium. So essentially, we know the amount of input force. So we know if we did a sum of forces for the total system, we know what the result should be. That's what this residual force is trying to iterate on and decrease till it's acceptable. So use this to track. There's a couple of the trackers you can look at. One is the displacement convergence. Another is the moment convergence. Moment convergence will only be active if you have shell elements or beam elements, something with a rotational degree of freedom. You can look at max DOF increment. This is how much is what's the maximum movement I see between iterations. So those are great things to look during the solve. There's a couple other things you can set up. The first would be, I suppressed it, so let me rerun this. But the first thing to consider would be this Newton-Raphson residual force. So you can turn that on if you highlight the solution of information. You can turn that on by specifying the number of residuals to store. This will essentially give you a color plot of where are the highest force residuals. That's helpful because when I'm looking at, let's say, my force convergence plot, if it's not converging, let's say it stopped here and didn't converge, I would want to know where the highest force residuals are because I know that my force residuals need to go to near zero to be accurate, at least below this blue line. So by analyzing these plots, we can see where those residuals occur. It could be because of mesh problems. It could be because of poor contact assignment. It could be because of high contact stiffness, really any number of things. But the way to turn those on is Newton-Raphson residuals 2, and they'll give you a color plot of where your residuals are mainly located. The next tool in your tool chest is if you right-click on solution information, you can assign trackers and probes, right? So if this was, here, let me actually clear this result. If this was unsolved, I can have deformation probes, I can have contact probes, I can have a deformation plot tracker, where this actually allows me to look at the deformed solution as the solve is still going on. And keep in mind, this is for converged substeps or load steps. It's not necessarily for, the deformation plot tracker is not necessarily for unconverged iterations. But I can assign a number of things, right? Particularly of interest here, if I were to assign a contact probe, I can look at number of contacting elements, I can look at pressure, penetration gap, etc. Generally, what I'm interested in, as you've probably picked up as I've been talking about this, is penetration. And I can look at this over the time, either over time or over the cumulative iteration of the solve. So I'm going to solve this again, and we can see, once this kicks off, I'm actually going to track the penetration during the solve for the different contacts. So what you're going to see is my red penetration, which is my one with the lowest stiffness, is going to have the most penetration throughout. The reason this would be beneficial is if you know what's an acceptable amount of penetration, potentially this would allow you to pinpoint it prior to running the entire simulation, and you might be able to terminate early, adjust settings, and then resolve. But you can look at any number of contact features with these probes during the solution. You can look at the iterations. I could look at the deformed solutions right now. Actually, this hasn't converged, sorry. So if I had substeps that had converged, I could look at the total deformation during the solve. I could look at my force convergence, right? It's getting close, it's about to converge, just converged. Those are all tools that are available to help convergence. Okay, so I'm just about up on time. So let me step real quick back to my slides. I just have a couple summary slides of different things to try and tools to use if you are encountering convergence issues. So first, convergence tools. Certainly convergence plots are a big one. Result trackers are huge. Newton-Raphson residuals are very helpful. And then the final I put here is experimental method. When you're having issues and troubleshooting them, always be careful to only be changing one thing at one time, right? Because it's not necessarily helpful to change a lot of things and then see if it works, because you don't know what may have helped or what may have hurt, right? So keep in mind, you should only be changing one thing at one time if you are having trouble. So additional things to look at. So certainly look at how the force convergence graph is behaving. You can check the solver output file, so it's a text file for any context information. Very often, warnings will pop up about too much penetration or change in status or things like that. It's reasonable to go through that and review. Yep, look at the results tracker. As I mentioned, look at the regions where there are high Newton-Raphson residuals, which can reflect possible problem areas. However, be careful because the one caveat I will say is high residuals don't necessarily mean incorrect solution or problem area. For instance, in my highest successfully solved beam bending problem, if I had stopped this early, I would have had the highest Newton-Raphson residuals on that beam. That's not because that result is inaccurate, it's just because that's where it's having trouble. So I have to look at how can I decrease that. That could be through refining the mesh. It could be through changing the contact stiffness, any number of things. But once we get it solved, we always have to make sure that the solution is accurate. Another approach, right, and this is something I do on a regular basis, is if I have multiple nonlinear contacts I'm all trying to solve at once, and I'm not sure what's causing my problem, then you can go in, just bond everything except one nonlinear contact, and solve the problem one at a time by turning the contacts on and off, so you know exactly where the issue is coming from. Another approach is if you're having contact challenge or convergence challenges associated with load changes. You can always use more substeps when you're applying a load, and or apply loads over separate load steps, right? So very often, if I have a setup with bolted joints, I'll apply the bolt pretension in the first load step and then gravity in the second load step. Because I found that if I apply gravity and bolt pretension all at once, sometimes it solves, other times it gives me challenges, right? So it's easier for me just to do it in two load steps and know it's going to work than try to troubleshoot the first one and make it work when it's just the simpler approach is just to go to two load steps. So just these are fairly basic points, but I think they're beneficial to make. So it is always more beneficial to start simple and add complexity as you go, right? Same rationale as the experimental method, so you can isolate the problems. Don't randomly change settings, right? I will agree, unless you know you have like a beam bending problem or something like that, you can always use recommended settings first and see what happens. If they just don't work, then you can start changing the settings using the tools. And then the final thing, caveat, is if you are using automatically generated contact regions, I would say be very, very, very careful and review them in depth to make sure they're all appropriately assigned. I know I generally never use automatically created contact regions just because of the risk of something being applied improperly and me not picking it up. So it's just one of those things. Be careful, make sure it's right and accurate prior to accepting a result is true. So I believe that should close out my final thing, and I already talked about this once. To verify accuracy for contacts, it's similar to a mesh convergence check, right? The difference is here, the normal stiffness is equivalent to like mesh density. So you would increase normal stiffness until you get to a point where you see, let's say if you're looking at stress, very little change in the max calculated stress. Or if you're interested in contact pressure, very little change in the max contact pressure. And once you get that, then you know it's a converged solution and accurate, or at least accurate enough. So this, I believe, is my last slide. Yes. Okay, so that was a whirlwind. I knew I blew through a lot of stuff very quickly, as I always do, and I apologize for that. Are there any questions?
Well, Steve, I don't see any questions on the chat room. So if nobody has any questions now, feel free to email them to me and I'll forward them to Steve. I know he covered a lot of material today, so it's hard to pick out one or two things to have a question on. So again, thank you, Steve, for preparing and doing that wonderful webinar. Just give it another minute. Okay, so like I say, I will be, posting our future webinars on ANSYS.com. We'll also post them at mallet.com, and also we'll send out emails to our regular attendees and customers directly, like I've always done. So feel free to email me with any suggestions if anyone has a particular topic they'd like to cover, even if it's a past topic, like this one that we can look at in a new light. So again, thank you, Steve, for presenting it. Thanks everyone for listening in. The recording will be available through our website. Everyone have a good rest of Friday and a good weekend. Thank you.